And this is my table of contents. As you'll see, I'm going to be talking a fair bit on experimental design before I come to heritability and coefficient of determination. The reason why I'm focusing on experimental design is mainly because I want to motivate why I'm focusing on pairwise differences in the assessment of heritability as well as the efficiency of experimental designs. And then I have two preliminaries on whether environments should be considered as fixed or random, and on what I call Stagewise analysis. So right into the examples. Here is an example of a design that's used in early generations when a number of seeds is so limited that you can't afford to do replications for the entries of interest. And so what you can do is do a replicated design for a few checks. So in this simple example, there's complete blocks with respect to the checks, and there's 6 complete blocks. And then you fill up the blocks, you augment the blocks with unreplicated entries. And the idea here is that you can use the checks to estimate the block effects and make adjustment for block effects for fertility gradients in the experimental field. And you can use them to come up with an estimate of the error variance, which you can then use to characterize the precision of the trial, compute standard errors, compute heritability, and the like. This is a balanced design with respect to the checks because it's complete blocks, but it should be emphasized it's incomplete blocks with respect to everything else, basically. Or on the whole, each block is an incomplete block with respect to the complete set of genotypes that are being tested. And this means that in the analysis, your estimate for the genotype is not going to be anything like a simple average. It's going to be an adjusted mean. Here's an extension of that idea that we've been working on, and this extension involves row-column blocking. So it's a row-column design because most of the time there are block effects associated with both rows and columns in the experimental field due to farm operations, depending on which direction the tractors drive during different types of operation. So it's always a good idea to cater for block effects in the rows, along the rows, and along the columns. And in a typical setting, you will start out with a given number of entries that you want to test that are going to be unreplicated. So how do you then come up with a design? Well, you need to also say what percentage of plots am I going to devote to checks? And that's going to set the stage. Basically, it's going to determine the total number of plots that you're going to be needing. And you need to think about the numbers of rows and columns you're going to have, and that's going to be constrained by a number of things. But anyway, assume that you settle for 22 rows and 10 columns. Then you can do the math. It's going to be 220 plots, subtracting the unreplicated entries. That leaves 47 plots for the checks. And since there's 4 checks, you need to somehow subdivide those 47 plots among the 4 checks. And it's odd numbers here, so there's going to be 3 of the checks will have 12 and 1 will have 11. So it's sort of a typical setting where you've got an odd number of unreplicated entries to begin with, and then you need to take it from there. So here's a row-column layout, and we want to adjust for row effects and column effects. So the design generation is going to be based on a model that has effects for rows and columns. But on top of that, we're going to subdivide the whole experimental field into what I call superblocks or superimposed blocks. And the reason for imposing those is to improve the evenness of the distribution of check plots in the finally randomized design. And the next step is to allocate plots that are going to take up the checks. So where do we place them? We place them in such a way that we have about even distribution across the rows. So every row you can check has 2 check plots. So this allows us to estimate effects for rows. There's just one row where there's 3 check plots because of the odd number of check plots. Each column has 5 or 4 check plots. And each of the superimposed blocks has 5, or well, in this case only 3 because it's a smaller superimposed block. I forgot to emphasize that the sizes of the superimposed blocks are unequal because there's all these odd numbers of rows and columns and check plots, so it doesn't add up so nicely. So we need to do something, well, more rough and dirty. But anyway, this is 3 blocking factors to account for. So the design generation needs to account for row effects, column effects, and the superimposed blocks. And then we need to allocate the checks, and we want to do it in such a way that the composition of each of the block factors is as balanced as it can be. Of course, the rows can't be complete blocks because there's only 2 plots, so they're going to be incomplete blocks. But we want to make sure that the pairings are about the same frequency for each pair. So C4 and C2 frequency should be similar to the frequency for other pairings of check plots appearing in the same row and so forth. And the same goes for columns. There's more than 4 in many of them, so they're more than complete blocks, and likewise for the superimposed blocks. And then the final step is to add on the unreplicated entries, and that's your augmented design right there with a fairly even distribution of the check plots. It's due to the way that the design is being generated, it's fully randomized, and you've got a randomization-based analysis that you can use. And the criterion that's used for searching a good design is called A efficiency, and it's a ratio of the mean variance of a difference for a contending design, which is the completely randomized design with no blocking, over the mean variance of a difference for the candidate design. So we try to maximize that efficiency factor. It's called the average efficiency factor. And the point I want to emphasize is that it involves the variance of a difference between 2 genotype means. And it sort of averages those across all the pairs. So it's really, any experimental design, any of the classical experimental designs that you use is based on a criterion that uses the variance of a difference between genotypes. Here's the second idea is Pyrrha design that's been around for more than 10 years now. The idea is to, instead of have replications for checks that you may not be primarily interested in, try and replicate some of the entries. Not all of them, but a proportion. So it's partial replication. Some of the entries get replicated. This is usually done in the context of multi-environment trials where in each environment or in each location you replicate a different subset of the entries of interest. So to give an example, if you've got 100 genotypes in 5 locations, at each location you can have 80 of the entries replicated only once and 20 replicated twice. And then each subset, you have 5 distinct subsets of entries, and each gets replicated in a different location. So across all the locations, the number of reps gets balanced out. That's the whole idea of Pyrrha. This has been originally proposed in a context where both the design and the analysis is based on geostatistical analysis. I love geostatistical analysis. I do a lot of that myself. But I'm a bit worried when the design is completely based on geostatistical models, because we do not know beforehand what the best fitting geostatistical model is going to be. There's a whole bunch of models to select from, so we need to actually settle for a model and use that to generate the design. But then at the analysis stage, it may turn out that's not the right model, so it's going to have to be a different model. So I prefer an approach where I have a classical block design that's randomized, so I have sort of a baseline to fall back to. I can then always explore spatial modeling, see if it adds anything. If it does, yes, take it. If not, I have my fallback position, classical randomized design, very easy to analyze, not much manpower or womanpower needed to do the analysis, do all the model selection, and so forth. So we've come up with an idea that does that for Pyrrha designs, combines the idea of augmented designs and Pyrrha designs. So the idea is to have a classical replicated design for the entries that will be replicated at any one location, such as an alpha design, basically, and then augment that in the same way as the classical augmented designs. But the main challenge is to how to do the augmentation, how to optimize the augmentation across all the locations in such a way that the whole thing is then optimized in terms of A efficiency. And this usually means that you want to optimize in such a way that the number of pairwise occurrence of the same pair of genotypes in the same block, that's the thing you want to focus on, that is balanced as much as possible between pairs of treatments or genotypes. So here's an example with 100 genotypes, 5 locations. Very briefly, so you would be replicating 20 of the entries. So here's basically an alpha design for 20 entries. And a block size that's very small, block size 2. So this is replicate number 1, replicate number 2, and each column within a rep is a block. So this is a block for genotypes 11 and 3 that will be replicated and so forth. And I have another of those for the next location. This is location 2, and I have another set of genotypes that gets replicated there. But these are all just basically alpha designs. And then we fill them up with unreplicated entries. And we do that using alpha arrays, the same idea that's used in the generation of alpha designs that have been pioneered by Emlyn Williams and Desmond Patterson. And here's a comparison of efficiency for P-rep design compared to some competing designs. One of them being an unreplicated design. Well, you do have replication, but you have replication at the level of locations. But each location is a completely unreplicated design. That's an interesting alternative. And then there's P-rep. And the other alternative is an alpha design with 2 replicates. And we use sugar beet data to estimate variance components, and then use those variance components in conjunction with superimposed alternative designs to compare efficiency. We used a mixed model for analysis with fixed effect for genotype and random effects for locations, G by E, reps, and incomplete blocks. So to assess efficiency, we looked at the mean standard error of a difference, which is just the square root of the variance of a difference. We also looked at heritability, and I'll come to heritability in more detail later. So whether you take heritability or you take the mean standard error of a difference, it's the same picture that emerges. Turns out that, well, the unreplicated design is actually pretty good, but you can really only compare designs that have the same total number of plots, so you can really compare those two. An unreplicated design versus a P-rep design. So the unreplicated design is actually slightly better than the P-rep design. And the same here, the alpha design, replicated, fully replicated, just 3 replications, is doing less well than the alpha design that's unreplicated, but has double the number of locations. So, and here's sort of the frontier, so this is plotting the standard error of a difference versus number of plots, and here's sort of the frontier, and you see that the unreplicated design actually does best, closely followed by P-rep, but the replicated designs are doing worst among those 3. So P-rep comes out second best. Why use P-rep? Well, this calculation assumes the same error variance in each location, but typically we have heterogeneity of variance. So we want to be able to account for that and weight the different trials accordingly. So and to be able to estimate error variance, you need some replication, and you can't have that with an unreplicated design. So that would be one case in favor of still using P-rep, although this result suggests that unreplicated is doing pretty good and doing best among alternatives here. And here's a replicated design, replicated with 4 replications, a row column design. This is from variety testing, not plant breeding trial, but this same setup. 25 genotypes, 9 rows, 11 columns. This is a row column design, a classical row column design. I think row column designs are great for the reasons that I've spelled out. But a problem in practice is that after randomization, it may turn out that you've observed clumping of some of for the replications for some of the entries, like 18 or 6. The replications are pretty close together in the design, although they're all in different rows and columns. So, plus you can have associations appearing repeatedly for the same pair of genotypes, like 1 and 19 here and here, and often there's good reason to try and avoid that sort of thing from happening. So, can this be improved upon in terms of what we call evenness of distribution and neighbor balance? Well, here's the reason why you would want to avoid these neighborhoods appearing repeatedly for the same pair. So due to frost damage, one of the entries may actually fail completely. And then what's often done in these trials is that the plot to the left and to the right is also omitted from analysis because there's neighbor effects occurring due to the fact that this plot in the middle failed completely. And then if you've got the same pairings appearing repeatedly, you're generating a lot of imbalance also for the remaining data, for the remaining entries. And you know, the poor guys who were just next to this one that failed just didn't do anything wrong, just that they were in the wrong place in the trial. So that's why there's good reason to try and avoid that. We use same ideas with the augmented designs, is to form column groups and also row groups, and at the intersection of both column groups and row groups, we have these superimposed blocks. And if we use those in the design generation, we can more evenly distribute the genotypes. And here's one resulting design, and I've just highlighted 3 treatments, those that were most closely clumped according to some of the measures that we computed. And you can see that they're still spread fairly well. This is based on a model-based search where we put in effects for the rows and columns and the superimposed blocks in the search, plus we added a spatial covariance within rows to improve neighbor balance and to improve the evenness in distribution. And here's another example where we used a direct search that doesn't use a linear mixed model, but instead uses a direct search routine that tries to avoid these types of self-adjacencies relative to the target plot, which were categorized into 6 different types. And then the numerical search tries to avoid these associations. Yeah, now moving on to getting closer to heritability, I want to emphasize that I'm taking environments as random, and I have done so in this model calculation that I've shown. And the reason I'm doing that is because I think, as I'm sure a lot of breeders here will agree, breeding is for a target population of environments, and the trials that are conducted represent samples from that target population of environment. And so we're mostly interested in average performance in the target population. If we think that something specific about an environment here as opposed to an environment over there, it's probably because there's stratification into zones, agroecological zones. If that's the case, fine, stratify, but still make sure you've got replication within each zone. And by replication, I mean locations. So, and then those locations within zones would be random. And what I'm doing. I'm emphasizing this because there's a lot of literature out there that treats locations as fixed. One example is the vast literature on the AMI and GGE biplots and models, which take both genotypes and environments as fixed. And there's a group in Australia that's been advocating this approach very much, where environments are fixed. And to be honest, I don't really understand why you would want to do that. Unless you have a scientific project where you specifically want to study causes of G by E. But from a breeder's perspective, I would always take them as random. The other issue I want to emphasize is that you can do stage-wise analysis, proceed in stages. That is, compute a genotype, analyze individual trials in the first stage, and in the second stage fit a model to the G by E two-way table. Or if you're going to do GWAS or genomic predictions, it could be a 3-stage process, where in the third stage you fit something to do GWAS or genomic prediction. This has been compared in a number of studies to single-stage analysis, where you set up a big model for plot data, and it can be done, and there's great software out there for doing that. But there's lots of good reasons for wanting to do it in a stage-wise fashion. I don't want to go into the details, but a lot of people prefer a stage-wise approach, and the point I want to make here, that's perfectly fine. That's perfectly fine. All you need to do, and that may be surprising to animal breeders here, use blue in all the stages but the last. And only in the last stage decide whether you want to use blue or black, depending on the status of your genotype main effect as fixed or random in a single stage model that you would formulate for the plot data in accordance with the objective of your ultimate analysis. So if you're going to do G-blob, it's going to be blob and random. But if you just want to have genotype means in a variety trial, it's fixed. But that needs to be decided only in the last stage. If you follow that through, you can show that your stage-wise approach is equivalent to a single-stage analysis. But not if you use blob all the way, because then you shrink, 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 and you would need to unshrink, which animal breeders do with deregressed proofs, but in plant breeding that's fairly uncommon. And you need to do weighting from one stage to the next to carry all the information forward, not only about the mean performance, but also about precision. And that's perfectly fine, and that's fairly common in the medical field where people do meta-analysis. That's also popular in many other areas, but in the medical field it's very popular, and it's developed there under the name network meta-analysis. So that's fairly standard and fine. And here's just an example from Genomic Prediction Project where we plotted single-stage mean versus two-stage results depending on how much information we carry forward. No information about the precision carried forward, pretty good correlation. Doing a weighting method that uses diagonal weights, using a single weight for every observation, and carrying the full information about precision, not only the variances of our adjusted means forward, but also the covariances forward. We get almost perfect agreement. Now, last couple of minutes, heritability. What's heritability? I'm not really going to make a big distinction between broad sense and narrow sense. It's genetic variance over phenotypic variance. And it has a lot of uses that I don't need to emphasize here. The question is, what is phenotypic variance? I need to put in this slide just to emphasize that I'm not really going to talk a whole lot about coefficient of determination, although when I sent in the title I was very excited about that topic because I'm working on it. I just want to say that heritability has the interpretation of a coefficient of determination of a regression of the genotype on the phenotype if you do a stage-wise approach and you have the genotype means in hands and ask what proportion of the variation in my genotype means is genetic. And that has the interpretation of a coefficient of determination. There's a lot of interest in that, in computation of R² for mixed models in general, and people interested in heritability, it's good to follow that parallel literature. So what's the phenotype? Is it a single plot observation? Is it a genotype mean in a single trial? A genotype mean in a multi-environment trial across locations? Or is it a blob? And how do we estimate the phenotypic variance? Seems fairly obvious questions, and it seems that it's all been answered. And this is what 90% of the papers that I see in plant breeding will use to define phenotypic variance for a multi-environment trial. Genetic variance plus interaction variance, G by E, over number of environments plus error variance over number of reps and number of locations. And it's based on a linear model with main effect for genotype, main effect environment, G by E, block effect, error. And this is not the model for an individual observation, but it's the arithmetic average for a single genotype, simple mean. And that would be the phenotype in this setting. It's actually also the blue, the best linear unbiased estimator under a fixed effects model, the best estimator you can come up with. We use that model. This is the variance of a mean. Or is it? Well, everybody says yes. This is about the variance of the individual genotype mean. So this is the phenotypic variance of that. But there's something missing there. There's an average of the environmental main effects. So the variance of the environmental main effects should show up here. It's really the variance of a mean. But it doesn't. Nor does the variance of the block effects. Something's wrong there. These are random effects. So they should show up if this were the variance of a mean. But it is half the variance of a difference between two genotypes. And that's where it all comes together with experimental design. We're interested in the comparisons among genotypes because we're making selections. So we need to look at those pairwise differences. If you compute the difference between two genotypes, this term and this term drops out. So that's the thing. So I think of this part of the phenotypic variance as half the variance of a difference. So the key, in a way, the key slide for my second part of the talk. But then this is a balanced setting, complete blocks. Hardly anyone uses complete blocks in a breeding program. We're very inefficient. Nor do we test all the genotypes in all the locations. It's rather more common to see something like this. Each rectangle is a 10 by 10 lattice design. Lots of lattice designs pieced together in 6 locations, 16 series of lattices. This is a more typical setup. Now, how do you define heritability or phenotypic variance for that? And all the designs that I showed you, and that's why I showed them, part of the reason for showing them was to emphasize that there's incomplete blocks in all of those. So you compute means. There will not be simple arithmetic averages. There will be adjusted means, adjustments computed using the model. So these means will all be correlated with each other. The variance will be heterogeneous. So it's not that easy. It's not that obvious how to define phenotypic variance. And that's why we came up with the idea to focus on these pairwise differences in defining heritability. So why not ask, what is the variance of a difference between two genotypes? For the true genetic effect and for the estimated genetic effects when we use blue. And that leads to this equation here, which involves the variance of a difference between two genotype means. And that's the same variance of a difference between two genotype means that features in the A efficiency criterion to find an optimal experimental design. And when you take the mean, well, the harmonic mean is what you need to take, you end up with this expression here, which we proposed 10 years ago, which involves half the average variance of a difference in the denominator here. And this in turn coincides with the usual formula for heritability. You can also do it for a blob, then the variance of a difference occurs in the numerator, and you can average that, and then it coincides with a measure that's been proposed by Brian Cullis in case genotypes are independent. You model genotypes with independent effects. It's not a new idea to look at differences. It's been put forward in these papers here in animal breeding and here in plant breeding. And they proposed a different measure based on differences or contrasts more generally. And to wrap up, here's 4 examples. A single completely randomized design in which genotypes are modeled as independent. A single alpha design where genotypes are modeled as random and independent. And then 2 more examples where genotypes are correlated according to kinship, or you might say you're doing genomic prediction, you're doing GBLUP using SNP markers. And a randomized complete block design, or a series of trials, each laid out as randomized complete block design. I'm going to skip that. Well, this is just to show that, this is for one of the examples, example number 4, you get a heritability for each pair, so you can plot those, and it's kind of interesting to see, well, the pairwise heritability is covering quite a range here. And it's good to just realize, well, there's not just one heritability value. Each pair basically has a different heritability in an unbalanced data set, and most of the trials that are done in big plant breeding programs will be unbalanced in one way or the other. You can average these pairs for each genotype, so you get heritability per genotype, which could be interesting information to look at. So I have here's some entries that I have very reliable information on, and others where information isn't that reliable. So that's good to look at. Here on this final slide, I have analyses for these 4 examples and a couple of methods here. Very briefly, with a completely randomized design with independent genotypes, it's a very simple setting. All methods produce the same result, except a method that I denoted as R squared. That's the reliability, or squared, well, it's a squared correlation between the true genetic value and its BLUP, which is commonly computed in animal breeding. It's slightly dipped down here. When kinship is used, sort of more diverse here. They're not doing the same thing anymore, so it does matter which one you choose. And one method that sticks out is Oki's method, which, to our surprise actually, we only did this a couple of weeks ago, produces a relatively low estimate of heritability. Although if you look at the equations, it looks like it's made to deal with correlated genotypes with kinship data, but it doesn't seem to be doing a very good job there. Yeah, so to summarize, optimal experimental design is based on the minimization of variance of pairwise differences. And computer-based search provides a great flexibility to generate all different kinds of designs using the optimality criteria based on pairwise differences. And heritability, likewise, can also be defined based on pairwise differences. It's intuitively appealing and easy to understand, easier to understand than Oki's method, which I always thought was the best method around, but involves eigenvalues and contrasts and a bit scary to look at. Can obtain heritability per genotype, and it coincides with the standard heritability in simple balance cases. And I think we're still exploring that the focus on pairwise differences provides a unified framework for design and analysis of multi-environment trials based on linear mixed models, and also to define a coefficient of determination for linear mixed models in general, which is the bit that I sort of skipped. A couple of papers, and thank you very much.